Hello, my name is Junbong Jang, and I'll present Fine-Tuning Language Models with Just 4 Passes by Sadiqa Maladi and others at Princeton University. And this is part of the journal group at Cocone M, the metaverse company. The motivation for choosing this paper is that the memory efficient zeroth order optimizer, Mezzo, saves 12 times more memory than fine-tuning method. As shown on the right on the bar graph, at 13 billion parameters, fine-tuning method requires 12 more GPU memory than Mezzo. And Mezzo takes about the same amount of GPU memory as the zero-shot method, and similar to in-context learning method. The second benefit of using Mezzo is that we can train Mezzo by non-differentiable loss functions such as accuracy, F1 score, and possibly user preference. Uh, Here you can see the stochastic gradient descent formula, and we train this trainable parameters by computing gradient loss. And but usually we have to compute the loss gradient analytically, but Mezzo can approximate it by 2 4 passes. Here are 3 godfathers of AI: Yoshua Bengio, Geoffrey Hinton, and Yang Li Kun, who won Turing Award in 2018. And Geoffrey Hinton actually came up with this 4 pass algorithm on December 2022. So this is very recent algorithm. So previously, for fine tuning, we had to first go through the 4 pass. Here, we input the data and goes through the deep neural network and outputs something, maybe classification, or it can be image. And we compute the loss against the GT ground truth image, for instance, or classification. And then for backpropagation, we compute the loss gradient and then update the parameters with the loss gradient. Here, eta is the learning rate. But in the 4 training method, we compute the 4 pass as before, but the difference is that we only compute the 4 pass twice without backpropagation. So here is the actual formula for training it. So simultaneous perturbation stochastic approximation, SPSA, estimate loss gradient by 2 4 passes. So here you have loss function here, which is the trainable theta plus the perturbation epsilon and z. So epsilon can be a very small perturbation like 0.01 in their code, and z is the normal distribution, sampled from normal distribution. And if you look at this 2 loss functions and visualize it, you can uh, it can be visualized as the gradient along the loss curve here. So 2 epsilon will be here, and L of theta plus epsilon 0 minus L of theta minus epsilon 0 can be shown as a y-axis here. So at the end, this part of the equation is this zero green line. Of course, you have z here, so you would have a little bit of perturbation in this z gradient. In this green gradient. And we have 2 z's here. I think it's because we want to keep, they wanted to keep the sign positive. But you can correct me later in the video, the comment section. So, okay, I think that's it. And then, so here is the 4 algorithm. I'll briefly go over. But first, the most important part, I think, is this setting the random seed part, because by setting this random seed, they saved a lot of memory. And I think actually other part of the algorithm is from previous works. So what is random seed? Well, instead of storing n number of values, we can store only one seed value. So if we just have this seed equals 1, then we just put it into the random number generator and it generates all these number. Of course, I just came up with this, but you get the idea. And if I set the seed equals 32 and pass it to the random number generator, you will generate a different combination of numbers, series of numbers, sequences of numbers. So in this way, you can save a lot of memory with random seed. So you use the random seed whenever it wants to sample something from the normal distribution. Okay, so I'll go to this perturb parameter part. So here we have data, trainable parameter, epsilon, which is 0.01, and s is a random seed. So we first reset the random number generator with seed s, and then for each parameter in this set of parameters, we sample some value from normal distribution with mean 0 and variance 1, and we perturb the data parameter with epsilon times z. Okay, and then after we do this twice, right? So we have L plus and then L minus from this perturbation, and this perturb at the end is just resetting the parameter to the original part, right? Because we perturbed the data to the epsilon direction once, and then 2 minus epsilon, and then you have to add epsilon again to go back to the original part, right? So, and then at the end we compute the projected gradient using this formula, which can be visualized as shown on the right, right? 2 epsilon here, and then L plus minus L minus here, right? Of course, this is just my visualization, so, and it's just in 2D, but yeah, you get the idea. And then we reset the random number generator with seed as again, and then sample values from normal distribution and compute this gradient, do this gradient descent using this projected gradient. So you can see we didn't actually compute gradient analytically, but instead approximated by a step before above here. So the formula here is just simple stochastic gradient descent, as shown here. So for training method, at the end is just almost mimics backpropagation by approximating this loss gradient. But the important part is that backpropagation goes updates the parameter in this order, right? From here to there to there to there. But using mezzo, you can just update the parameter independent to each other. Because like you don't need the loss gradient here. You don't need to compute the loss gradient here to compute loss gradient here, and so on, if you use mezzo. So here are the results. First, the important part is that the accuracy of mezzo is similar to the fine tuning. So here you can see the mezzo in dark green is similar to fine tuning method. Well, it's sometimes similar or sometimes a bit worse in some data sets and some tasks, and sometimes mezzo is better. So it's can't say for sure, but mezzo is very close to the fine tuning in terms of accuracy and F1 score. And mezzo is much better than a zero shot or in context learning methods. When they trained the OPT 13 billion parameter model, which is very large. And this is for another experiment when they trained relatively smaller model, Roberta A large. You can see that again, mezzo is similar to fine-tuning method in terms of accuracy. You can see that regardless of using mezzo, mezzo LoRa, or mezzo prefix, the performance is similar. And the authors also mentioned that they train at similar speed regardless of number of parameters, which is interesting. The reason is that they also had this theory section on convergence rate, and I wouldn't go deep into it because I didn't actually completely understand it. So just to briefly say what they theorize is that under strong assumption as shown below, convergence rate of zeroth order SGD, stochastic gradient descent, does not depend on the number of parameters. Instead, the slowdown factor only depends on the effective rank of the Hessian. So Mezzo can train large language models, but slower than backpropagation by the slowdown factor, which is the effective rank of the Hessian. Yeah, so I would say just choose prefix or LoRa or just simple mezzo based on how high accuracy it is, instead of like worrying about their size, number of parameters, trainable parameters. So that's one good thing. And here's the result on training on non-differentiable loss function. And you can see that it's actually better to use differentiable loss function, which is cross entropy. But it's interesting that we can still use accuracy or F1 as a trainable training loss. And this is the most important result, I think. Mezzo uses the same amount of memory for both training and inference. So this is the graph I showed you in the beginning of the video. So Mezzo uses much less, like 12x less memory than fine-tuning. And similar to the zero shot, which is inference. And figure 4 shows that when using like A100 GPU, you can only fit 2.7 billion OPT model for when fine tuning. But when you use inference, you can fit 30 billion OPT model. And since Mezzo uses the same amount of memory as inference, Mezzo can fit 30 billion OPT model on A100 GPU. So which is very significant amount of memory saving. So in conclusion, while using much less GPU memory, Mezzo yields similar accuracy to fine-tuning method, and Mezzo can quickly train very large model, up to 66 billion parameters in their, which they tested in their experiments. And GPT-3 has 175 billion parameters, but unfortunately, they did not test it. They just projected without actual testing. But with enough GPU memory, backpropagation can train faster. So if you have enough money, I guess you can just have a bunch of 800 GPUs to train GPT-3 instead of using Mezzo, which might yield lower accuracy and much longer training. But I would say when you, for cost in terms of saving cost, you can train very large model on a single RTX 39 GPU, for instance. So that's in our case, I guess I would say that it's better to have decent model while like using much less money than spending lots of money to have like 1% accuracy improvement. So I guess that's when we would use Mezzo. And there's another a useful way to use 4 path, but I would keep it secret for now since we are gonna work on it. So thank you for listening, and if you have any questions or things to correct, then please leave please tell me or leave comments in the comment section. Okay.